Now it is time for calculating the expected value and the variance of the normal random variable. Now, maybe after this normal distribution story, after this adventure on the normal distribution, maybe you have forgotten that all random variables have an expected value and variance, okay? Now, we have calculated the expected values and the variances for all remaining spatial random variables that we have covered in this lecture. Now, we are going to do the same for the normal random variable as well, okay? Now, but it is going to be a little tricky, okay? It is theoretically going to be a little hard. So this time, I mean, remember now, as we solve the questions, as we solve practical questions, we are preparing ourselves for the exam, okay, for the exam. But as we study theoretical proofs and theoretical expressions, then we are preparing ourselves for our future studies. So students do not understand the distinction between these two. Okay, every practical question that we solve prepares us for the exam. But our main objective is not for preparing the exam. Our main objective is to prepare for our future learnings. Okay, everything that we learn is going to be used in our future learnings. Okay, so theoretical background of this course is also important, even though I am not going to ask any mathematical proofs in the questions in the exams. The theoretical background is also important. Now, I want to compute the expected value of a standard normal random variable. Okay, I'm going to start from the simple. I'm not going to calculate any normal random variable, just the simplest of the ones, the standard normal random variable. I am going to calculate its expected value, and then I am going to calculate its variance. So let's just first focus on the standard normal random variable. Okay. So remember, this was the probability density function of the standard normal random variable, denoted by Greek letter phi x, which is 1 over square root of 2 pi e to the power minus x squared over 2. Now, what I am going to do, remember, how do I calculate the expected value? You know, I calculate the expected value by multiplying x for a continuous random variable. I am going to multiply x with the probability density function and integrate it from minus infinity to plus infinity, right? So what I am going to do this, I'm going to solve this integral to calculate the expected value. Okay, that is my expected value. Now, but before that, before solving that integral, let's take the first derivative and the second derivative of this phi x function. Maybe we will find something useful to solve that integral. Okay, so let's take the first derivative of this function. You know, the first derivative of exponential functions are the same as itself. However, at the power of this exponential function, we have another function. Therefore, we need to apply the chain rule, and we need to multiply this function with the first derivative of the power. And the first derivative of power is minus x, right? So the first derivative of the power is minus x. So I am going to multiply this function itself with minus x, the first derivative of the power, and that is going to make the first derivative of this function to equal to minus x times the function itself. So the first derivative of phi x is itself multiplied with minus x. Okay, so this is the first derivative of the probability density function of the standard normal distribution. So let us check that if the first derivative is equal to minus x times phi x, then x times phi x will be equal to minus the first derivative of phi x. So according to this equation, according to this result, x times phi x is equal to minus the first derivative of x, which means this integral is actually equal to minus phi derivative x. Okay, now I think this is much easier to solve this integral because we are going to integrate the derivative of a function, which is exactly going to be equal to phi x, right? Minus phi x, obviously. Minus phi x at minus infinity and plus infinity, right? So if x times phi x is equal to minus phi derivative x, then the above integral is going to be the same as this integral, and the integral of a derivative is the function itself. So this is the easiest way of explaining the solution of this expected value integral. Okay, now let's check the second derivative. Most probably the second derivative is going to be helpful in variance calculation. Now, what is the second derivative of the first derivative? So the first derivative is minus x times phi x. If you take the first derivative of the first derivative, we are going to get the second derivative. So we have a multiplication here. The first function is minus x and the second function is phi x. So how do you calculate the first derivative of such a product? We calculate the first derivative of the first function times the second function, which is minus 1 times phi x, plus the first function itself times the second derivative, the first derivative of the second function. Okay? So remember now, the first derivative of the first function times the second function plus the first function times the first derivative of the second function. And the first derivative of the second function is already calculated here, minus x phi x, right? So we write it here, and then we get x squared minus 1 phi x as the second derivative. And from here, x squared phi x is going to be equal to the second derivative plus the function itself. Okay, so x times phi x is this, and x squared times phi x is equal to that. Now check that out. What is the expected value? The expected value of a standard normal random variable. It is x times the standard normal PDF from minus infinity to plus infinity integrated. And because x times phi x is equal to minus phi derivative x, the integral will give us minus phi x plugged in the infinity and minus infinity values. Okay, so let me show you the minus phi x. So it says minus phi x function, right? So this is the real line, and the minus phi x function is this, right? It is this. This is minus phi x function. And at minus infinity and plus infinity, it is always equal to 0, right? Because of the convergence. And therefore, we have 0 minus 0, which indicates that the expected value of z is equal to 0. In fact, there is no need to do that, because you see pages ago, for standard normal distribution, when I draw the PDF of the standard normal distribution for the first time, you can see this PDF is symmetric around 0. If it is symmetric around 0, then this means the expected value should be just in the middle. Okay, for symmetric PDFs, the expected value should be in the middle. This means the expected value of z, standard normal random variable, is 0. Now, if the expected value of a standard normal random variable is 0, so let's check the result. If the expected value of a standard normal random variable is 0, then what is the expected value for any normal random variable? Okay, remember now, for any normal random variable, if we apply this standardization, we are obtaining a standard normal random variable, right? So if you subtract the location parameter from a normal random variable and divide the difference to the scale parameter, you get a standard normal random variable. But this equation is also true in the opposite direction. If you just take this denominator as a multiplier to z and subtract the location parameter from the multiplication, then this means if you multiply a standard normal random variable with a scale parameter and add the location parameter, then you are going to get a normal random variable with this location parameter and scale parameter. So this is standardization, and this is the inverse of standardization. You can go back to the original random variable by multiplying standard normal random variable with the original scale parameter and add the original location parameter. So what is expected value of x? then expected value of x is equal to expected value of sigma times z plus mu. And remember now, in the end of chapter 4, you can check page 72. We have said that the expected value of a linear transformation is equal to the linear transformation of the expectation, where expected value of z is equal to 0 from that proof. Therefore, the result is mu. And the expected value of a normal random variable is always equal to its location parameter. In fact, this is not surprising at all. If I go back to slides earlier again, if you check the probability density function of any normal random variable, you will realize that it is symmetric around the location parameter, and the location parameter is therefore equal to the expected value. Okay? So you see mu, the location parameter, is also equal to the expected value in a normal random variable. So